Hello. So today we're going to look at differentiating the trig functions. Some of these we haven't seen yet, and we usually would have because we would have finished the trig internal, but we haven't managed to do that. So some of them will look pretty weird, but don't panic too much. Hopefully we'll do the internal later in the year, and some of this will make a bit more sense. So these are our 6 trig functions. Sine of x, cos of x, tan of x, sec of x, cot of x, and cosec x. So the first 3 we hopefully have seen, sine, cos, and tan. The next 3 are actually just the top 3 inverses. So over here you can see sec is 1 over cos, cot is 1 over tan, cosec is 1 over sine. Now when we do the trig internal, you'll see why we need these. It pops up a lot in algebra and being able to manipulate them, and there's lots of kind of rules and formulas to do with them. So they are actually very important. So each of these has a derivative. They all have a graph. Each of these 6 functions have a graph. We could graph them all, but we're not going to do that. It'll waste too much time. But they all have a graph, and they all have a gradient formula for that graph, which is its derivative. And they all kind of stay within themselves. So sine differentiates to become cos, cos differentiates to negative sine, tan becomes sec squared, and remember early on in algebra, sec squared just means sec times sec, it's just sec times itself. Sec differentiates to sec tan, cot differentiates to negative cosec squared, and cosec differentiates to negative cot cosec. Good. But just like our other things that we've been doing lately, we do need the chain rule, because if we differentiate something more than just sine x, sine of g of x, for example, or sine of 5x or sine of x squared or something, we do need to know how to differentiate that. So the rule is sine of g of x differentiates to g dash, or the derivative of the inside function, multiplied by what sine would differentiate to become. So sine differentiates to cos, so that's why there's a cos of g of x there. This is the same for all 6 of these functions. I'll do one other example, but it's the same method for all 6. So if we had sec of g of x, we differentiate that. Again, it's the middle stuff differentiated, g dashed of x, multiplied by what sec would differentiate to. So sec would differentiate to sec tan. And it's just whatever is inside there stays inside there for the derivative of sec. So you'll see the pattern for all the things we differentiate, the pattern continues. It was same for E, same for ln. All of these trig functions have the same pattern there. So let's do a few examples. Last one might be a little bit tricky, but I'll give it a go. Alright, I'll just make sure everything is in the screen. Alright, so if we differentiate cos 3x, so we're going to be using our chain rule, and we're going to be using what cos differentiates to become. So f dashed of x will become this differentiated, 3x differentiated just becomes 3. And we multiply that by cos differentiates to become negative. So this is going to become negative sine 3x. I have to be a little bit careful here with this times a negative thing. If in doubt, put it in a bracket. Or we could rewrite this as negative 3 sine 3x. Alright, second example. So we have 2 things separated by a minus. So we do each thing individually. Cot of x is nothing extra there, so it's just going to go exactly to what cot differentiates to become. So y dash will become negative cosec squared of x minus cosec x squared minus 4. So cosec, we have to differentiate this inside stuff, so x squared minus 4 will differentiate to become 2x. 4 goes away to nothing. Times by what cosec differentiates to become, which is negative cot times by cosec. So this can be tidied up a little bit. It's negative 2x times by negative cot, so that could actually become positive. So we'll rewrite this as negative cosec squared x plus, that's my negative 2 times my negative cot, 2x cot x squared minus 4 cosec x squared minus 4. And that's our final answer. Last one. So again, two things separated by a plus, so we'll do each of them individually. So 2 at the front just tags along for the ride. Tan 5x over 2. So we just have to be careful here. On a side note, we might think about what the derivative of 5x over 2 is. So if we're trying to differentiate that, essentially this could be rewritten as 5 over 2x. Now it's similar to just like 10x or 4x or 8x when we differentiate that. So if this is y, y dash would become just 5 over 2. Just like if it was 10x, it becomes 10. 5 over 2 becomes 5 over 2. So differentiating this, it becomes that differentiated, which is our 5 over 2. This 2 is actually at the front tagging along for the ride, so that just multiplies there. And then what does tan differentiate to become? It becomes sec squared. Sec squared 5x over 2. So that 2 is at the front. Differentiate that, which is 5 over 2, multiplied by tan differentiated, which is sec squared, plus 4x differentiated, which becomes 4. Lastly, that's 2 times by this 5 over 2. The 2's can actually cancel there, and we'll just have 5 sec squared 5x over 2 plus 4. And that's our final answer. Those are our examples. We're going to learn a few more rules in the following lessons, so there is quite a bit to cover in the differentiation topic. All right.